Our universe is a vast and enigmatic place, filled with wonders and mysteries that boggle the mind. We gaze at the night sky, filled with twinkling stars and distant galaxies, each one a beacon of light in the dark expanse. But what we see is only a fraction of what's really out there. The visible universe is just the tip of the cosmic iceberg. Lurking in the shadows is a mysterious substance called dark matter. Dark matter is invisible, a ghostly presence that doesn't interact with light. It doesn't emit, absorb, or reflect light, making it completely undetectable by our traditional means. So we can't see it directly with our telescopes. Despite our advanced technology, dark matter remains elusive, but we know it's there because of its gravitational effects on the visible universe. It bends light from distant stars and galaxies, a phenomenon known as gravitational lensing. Like a phantom hand, dark matter tugs on stars and galaxies, influencing their movements in ways we can't explain with ordinary matter alone. It's as if an unseen force is orchestrating a cosmic ballet. Imagine a cosmic dance floor where galaxies twirl and spin, their movements choreographed by an invisible partner. Their movements should be governed by the visible matter we see: stars, gas, and dust. These are the elements we can observe and measure. However, astronomers have found that galaxies are moving much faster than they should if only visible matter existed. This discrepancy has puzzled scientists for decades. It's like an invisible force is giving them an extra push, propelling them at speeds that defy our understanding of physics. This missing mass, this unseen force, is dark matter. It makes up about 27% of the universe, yet we know so little about it. The quest to understand dark matter continues, as scientists around the world strive to uncover its secrets and reveal the true nature of our cosmos. The story of dark matter begins in the 1930s with a Swiss astronomer named Fritz Zwicky. Zwicky was a visionary in the field of astronomy, known for his unconventional ideas and groundbreaking theories. Zwicky was studying the Coma Cluster, a massive gathering of galaxies located millions of light-years away from Earth. This cluster, with its vast number of galaxies, presented a unique opportunity to study the dynamics of the universe on a grand scale. He noticed something peculiar. The galaxies were moving much faster than they should based on their visible mass. According to the laws of physics, the gravitational pull from the visible matter alone wasn't enough to account for these high velocities. Zwicky proposed the existence of dunkle materie, or dark matter, to explain this discrepancy. This was a revolutionary idea at the time, suggesting that there was an unseen substance exerting gravitational forces. He suggested that this invisible substance was providing the extra gravity needed to hold the cluster together. Without this dark matter, the galaxies would simply fly apart, unable to maintain their current structure. Decades later, in the 1970s, Vera Rubin provided even stronger evidence for dark matter. Rubin, an American astronomer, was known for her meticulous and detailed observations. Rubin was studying the rotation of spiral galaxies, including our own Milky Way. She focused on the movement of stars within these galaxies, particularly those located on the outer edges. She found that stars on the outskirts of these galaxies were moving much faster than expected based on the visible matter alone. This was a significant finding, as it suggested that there was more to these galaxies than met the eye. Rubin's meticulous observations, coupled with Zwicky's earlier work, solidified the case for dark matter. Her data provided the much-needed confirmation that Zwicky's dark matter theory was not just a speculative idea, but a fundamental aspect of our universe. It became clear that our universe was filled with a mysterious substance that we couldn't see or fully understand. This dark matter, though invisible, plays a crucial role in the formation and behavior of galaxies, shaping the very structure of the cosmos. The evidence for dark matter extends far beyond the movements of individual galaxies. It's also imprinted on the largest scales of the universe, in the way galaxies cluster together and in the cosmic microwave background radiation, the faint afterglow of the Big Bang. Imagine the universe as a giant cosmic web, with galaxies strung along filaments of dark matter. These filaments act like a scaffolding, providing the gravitational glue that holds the universe together. Without dark matter, galaxies would be scattered randomly, and the universe would look very different than it does today. The cosmic microwave background radiation provides another crucial piece of evidence. This radiation, which originated just after the Big Bang, contains subtle temperature fluctuations that reflect the distribution of matter in the early universe. These fluctuations tell us that dark matter makes up a significant portion of the universe's total mass and energy. So, if we can't see dark matter, how do we know what it's made of? This is one of the most intriguing questions in modern astrophysics and particle physics. Scientists have proposed several candidates, each with its own unique properties and ways of interacting with the universe. These candidates are theoretical particles that could explain the mysterious nature of dark matter. One of the leading candidates is the weakly interacting massive particle, or WIMP. WIMPs are fascinating because they could potentially be detected through their rare interactions with ordinary matter. WIMPs are hypothetical particles that interact very weakly with ordinary matter, making them extremely difficult to detect. Despite this, their potential mass and weak interactions make them a prime candidate for dark matter. They are thought to be much heavier than protons and neutrons, the particles that make up atoms. This significant mass could account for the gravitational effects attributed to dark matter. Another candidate is the axion, a much lighter hypothetical particle that was originally proposed to solve a problem in particle physics. Axions are intriguing because they could also explain certain astrophysical phenomena. Axions are thought to interact even more weakly with ordinary matter than WIMPs, making them even more challenging to detect. Their elusive nature requires highly sensitive and innovative detection methods. Scientists are actively searching for WIMPs, axions, and other dark matter candidates using a variety of techniques, from underground detectors to particle accelerators. These experiments are designed to capture the rare interactions of these particles with ordinary matter. The hope is that by studying the properties of these hypothetical particles, we can unlock the secrets of dark matter and its role in the universe. Understanding dark matter could revolutionize our comprehension of the cosmos, shedding light on the unseen forces that shape galaxies and the large-scale structure of the universe. The search for dark matter is a multifaceted endeavor, involving a range of sophisticated tools and techniques. Astronomers use the phenomenon of gravitational lensing to map the distribution of dark matter in the universe. Gravitational lensing occurs when the gravity of a massive object, such as a galaxy cluster, bends the path of light from a more distant object behind it. This bending of light acts like a cosmic magnifying glass, distorting and amplifying the image of the background object. By studying the distortions caused by gravitational lensing, astronomers can infer the presence and distribution of dark matter, even though it cannot be seen directly. Meanwhile, deep underground laboratories are being used to search for the faint signals of dark matter particles interacting with ordinary matter. These labs are shielded from cosmic rays and other sources of background radiation, allowing scientists to look for the rare events that might signal the presence of WIMPs or axions. The quest to understand dark matter is one of the most compelling challenges in modern physics and astronomy. It represents a profound gap in our understanding of the universe, and its discovery has the potential to revolutionize our view of the cosmos. Dark matter plays a fundamental role in the evolution and structure of the universe. It provides the gravitational scaffolding upon which galaxies are built and influences the cosmic web's intricate tapestry. By unraveling the mysteries of dark matter, we can gain a deeper understanding of the universe's origins, evolution, and ultimate fate. The search for dark matter is a testament to human curiosity and our relentless pursuit of knowledge. It is a journey into the unknown, driven by the desire to comprehend the fundamental nature of reality. And while the answer to the mystery of dark matter remains elusive, the pursuit itself continues to illuminate our understanding of the universe and inspire future generations of scientists and explorers.